Morning, folks.
Morning, Papa.
Oh, thank you. I'm stealing some time from Vladimir because I didn't get to finish my storyline last time with the network flows. So I'm going to be here for about 10 to 15 minutes just to get it to a point where you can appreciate some of the things that you'll be seeing in the next phase of the course. What I am about to talk about is the foundation of what some of you may have heard as SPICE, which is a computer-based analysis system for circuits. It was developed right here at Berkeley. So it was modeling circuits as graphs, which enabled entry of the parameters of the circuit into a computer decades ago that enabled engineers to analyze circuits on the computer. So it has had a very serious impact on circuit analysis. Okay, so I was talking about, I'd drawn a network of 4 nodes. And soon these circles are going to be turning into just dots when you get to circuits. But right now I'll keep them this way. I drew connections between these nodes, and I ascribed an orientation to each of the edges. So an arrow going from node 1 to node 2 simply means that the positive direction of flow is when something flows from node 1 to node 2. If the flow is a flow of electrons, like electrical current, then it means that current in this direction is considered positive. It does not mean that nothing can go in the opposite direction. So current can flow in the opposite direction, but if it does so, then its sign is a negative sign. Okay? Just like you would measure speed. Speed along a particular direction, you specify as a positive direction, and the opposite direction would be a negative direction. Okay, and the way I'm going to label the edges is the way a dictionary is listed. So I'm going to start with the lowest order one to the highest, from the lower numbered one to the higher number one. I draw the arrow to the higher number one. So notice here, the arrows are all from 1 to 2, 1 to 3, and 1 to 4. And then 2 to 3, 3 to 4, and that's it. I'm done. So I'm going to label these as edges 1, and then 1 to 3 will be edge 2, 1 to 4 will be edge 3, this is edge 4, and this is edge 5. So if you don't have to do it this way, okay? In fact, Gil Strang doesn't do it this way in the relevant section where he covers this stuff. And a lot of times in network analysis, you won't see things labeled this way. But it's convenient to do it this way because it will give a special structure to the incidence matrix that I started filling up for you last time. So if you think of 1 and 2 as analogous to the letters A and B in the dictionary, then this will be edge 1. Edge 2 will be from 1 to 3, just like you would go from A to C, and so on. And you list these edges the way you would list words in a dictionary, okay? Now, not all of the combinations are listed. Clearly, I don't have an edge from 2 to 4, okay? The other thing I'm going to do is that I'm going to construct a matrix associated with this graph. The matrix associated with the graphs that we've been studying so far were square. I'm going to construct a different type of matrix for this type of work. It's not necessarily square. In fact, in this case, it will be 5 by 4. So let me go to a new board. So I'm going to construct an edge node incidence matrix. Just like the state transition matrix that you studied in all the graphs that we've been looking at so far, you should be able to go from the graph to the matrix and back. If I give you the matrix, you should be able to draw the graph. If I give you the graph, you should be able to draw the matrix. And this is how it works. So the matrix, I'm going to call it F, is going to have a column corresponding to each node. So node 1, node 2, node 3, and node 4. And a row associated with each edge. 4, and let's extend it down a bit. 5. So if I have n nodes and m edges, this matrix will be an m by n matrix. And ordinarily, this will not be a square matrix. The way I'm going to fill the entries in this matrix is as follows. I look at edge 1 right there, okay? I'm going to put a 1, so I look at which nodes edge 1 is incident on. So incident means its endpoints are the nodes on which it is incident. So edge 1 is incident on nodes 1 and 2. Node 1 is where the arrow is going out of. Node 2 is where the arrow is going into. Edge 1 is not incident on node 3 and is not incident on node 4. If I want to go back to the previous board, what I have here is I put a +1 here and a -1 here. I put a +1 here and a -1 here. Okay? That's how I fill the entries in the incidence matrix. So what is edge 2? What nodes are edge 2 incident on? 1 and 3. Which one takes the 1? 1. And 3 takes the -1. Edge 2 is not incident on node 2, and it's not incident on node 3. And I'm going to continue this way, filling this matrix. So edge 3 is incident on nodes 1 and 4. 1 takes the +1, and -1, and node 4 takes the -1. Edge 3 is not incident on nodes 2 and 3. And I do this for the other nodes as well. So edge 4 goes from 2 to 3. So 2 takes a +1, and 3 takes a -1. These other two guys take zeros. And edge 5 goes from 3 to 4. 3 takes the +1, and 4 takes the -1. Okay? So given the graph, you should be able to construct the incidence matrix. And similarly, from the incidence matrix, you know that there are 4 nodes and 5 edges. The non-zero entries tell you which edge connects which pair of nodes. So if I just give you this matrix, you know that edge 1 is between node 1 and node 2, and node 2 takes the arrow. You know that edge 2 connects nodes 1 and node 3, and edge 3 takes the arrow. And then this way you can construct the graph diagram. Okay, is everybody with me so far? Cool. Now, notice there's a very special structure with this matrix. First of all, it's sparse. There are a lot of zeros in this matrix. And in large circuits, there will be a lot more zeros. The second feature is that each row sums to 0. Right? In each row, I only have 2 non-zero entries. They're 1 and -1, and they sum to 0. So F times the all ones vector gives me the 0 vector. Now that tells me that the rank of the matrix is at most, how many columns do I have? In terms of symbols. N. I have n nodes. Okay? I found a non-zero, non-trivial vector in the null space. So the rank can be at most n-1. In fact, I'm going to claim that the rank of F is precisely n-1. And the way I'm going to see that is by tearing out some of the edges in this graph. So based on what we've said so far, I can't make this conclusion. This conclusion is stronger than what this equation indicates. This equation, all it says is that the rank can be at most 3. I can find at most 3 columns that are linearly independent. Because I don't know if there are other non-trivial vectors in the null space. But I'm going to give you a qualitative description that will hopefully convince you that this is the case. So n minus 1 is a magical number associated with every graph. N minus 1 is special. It is the number of edges in a spanning tree of the graph. What? Spanning what? A tree is a graph that has no loops. You cannot find any circuit in that graph. Okay? There is no closed loop. So there are a couple of ways I can create a tree out of this graph by eliminating edges. So one way I can do it is by eliminating edges 2 and 3. If I eliminate edges 2 and 3, I will have the following tree. Here, here, and here. And as far as the spanning tree is concerned, the orientation of the edges doesn't matter. All you want are connections, are edges, the existence of an edge between a pair of nodes. Now, if you look at this, you'll have 1, 2, 3 edges, right? And that's n minus 1. N minus 1 edges in this tree. In some elite circles, this kind of a graph is called a linear chain for obvious reasons. It's a series of nodes connected by edges. Another way I can construct the tree from this graph is by eliminating edges 4 and 5. So I can write 1, 2, 3, 4, and keep this guy, and keep this guy. You can see that node 1 in this case can be thought of, if I were to rotate these edges, can be thought of as the center of a star. This type of a graph is called a star graph. It doesn't matter what kind of a tree you construct, as long as you eliminate the number of edges that are necessary so that you don't have any loops. Notice in each of these, there is no loop. I can't follow a path and come back to the original point. Okay? And each of these cases has n minus 1 equals 3 edges. Okay, now why is this significant? Well, look at the corresponding rows of, let's say, the linear chain tree. By the way, the word spanning means that you have to include all the nodes. Spanning tree means it's a tree, it's a graph that is a tree. It doesn't have any loops, but it covers all the nodes in my original graph. And each of those 2 graphs has that property. Now, so what are the edges in this linear chain? I have E1. Let's label them properly. This is E4, and this was E5. Huh? So if you look at the first row, and you look at the 4th row, and you look at the 5th row, there is no way you can linearly combine these in a non-trivial way to get 0. For one thing, look at this 1 here. Neither of these 2 guys has a non-zero entry there. So there's no way I can combine these 2 to cancel the 1 here. If you look at the star graph, it's edges 1, 2, and 3. Okay? So now if I look at edges 1, 2, and 3, these 3 rows, notice the minus 1 in edge 1 cannot be canceled by a combination of rows 2 and 3. So these 3 rows are linearly independent. Okay? And you can try this with any tree that spans the original graph, and you'll find that the rank of the matrix, there are n minus 1 independent rows. And that's why we said that the rank of the matrix is n minus 1. Now let's look at the 4 fundamental subspaces for this matrix. So the matrix takes vectors in Rn, which is R4 for us, and maps them to Rm, which is R5 for us. So here we have the null space. And the dimension of the null space we found was, so the dimension of the row space, this is the row space, remember? Row space. The dimension is the rank of the matrix, which is n minus 1. If that's n minus 1, then the dimension of the null space is 1. And we've already found that vector. We've already found the vector in the null space of F. On this side, you have the left null space, and you have the column space. The column space, its dimension is, of course, the rank of the matrix, which is 1. Which is n minus 1. So what does that make the dimension of the left null space? These two must add up to what? M. So the dimension of this is m minus n minus 1, which is m minus n plus 1. And there is something special about that number as well. If you compute this number for our particular graph, what do you get? What's m? 5. What's n? 4 plus 1 is 2. Now look. Let me get a color. Two is the number of independent loops in my network. This is the number of independent loops. It's the number of edges I keep adding to get all the necessary equations that I need to solve the system. So if it's a circuit, what do I need, by the way, if it's a circuit? What else did I define on these nodes? I defined the flow. So there was a flow associated with each edge. In electrical terminology, that would simply be current. So this would be Y5, Y2, Y3, and Y4. What else did I define on this network last time? No, the orientation, well, it's given. For each node, I had a potential. Potential 1, potential 2, potential 3, potential 4. Associated with each node is a potential. If this is a physical system, let's say the nodes represent points along a mountain path that you take, and you've got this device that measures your potential energy at those points as you're crossing that point, then those will be your potential energy. Right? And if you complete a loop, the change in your potential energy will be 0. In electrical terminology, if you complete a loop, the change in electrical potential energy will be 0. So to solve the system, you need M what? M flows, no? You need to know the flows. And you need, I'm going to claim n minus 1 potentials. For a total of m plus n minus 1 unknowns. With potentials, I don't need n potentials. Think about the physical analogy. You can have a reference potential energy point. Now that reference point might be either on the graph or it might be somewhere separate. So if this is a mountain and you're going between these four nodes, according to some flow direction, your reference point might be one of the nodes, or it might be, say, the sea level, where that would be the corresponding to potential energy 0. If you take the reference point outside, then the behavior of the system doesn't change if some giant monster comes here and lifts the entire mountain and takes it to a higher or lower elevation. Why? Because of this. This equation is what allows us to go with n-1 potentials. And let's see how that works. And I think I need to wrap up soon after that and let Vladimir do some talking. So what is F times P? What happens when I multiply? So P is the potential vector. P1, P2, P3, and P4. If I multiply F by P, what do I get? What's the top entry of the vector? P1 minus P2. What's the second one? P1 minus P3. What's the third one? P1 minus P4. And the other two? P2 minus, louder, P3. I'm an old guy. My hearing isn't as good as when I was your age. And the last one? P3 minus P4. Can you interpret each of these differences? What does P1 minus P2 mean? P1 minus P2. It means the change in potential energy across the corresponding edge. Okay? That change in potential energy in electrical terminology we label as in terms of voltage drop or voltage. 4, 5. The null space is when I have the null space is the vector of all ones or any scalar multiple of all ones. So when this is 0, 0, 0, 0, 0, 0, what does that mean? That P1 is equal to, and P2 is equal to, and P3 is equal to, and P3 is equal to, which means all the potentials are the same. That means if you change the potential across the board, along all the nodes, by a certain constant amount, up or down, nothing changes in terms of the behavior of the circuit. And the flows are the same. The flows depend only on the change in potential across an edge. So the value of y1 is related to that potential drop or increase along the edge. So that's why we tend not to take a reference outside of the circuit. In the circuits that you'll be analyzing in this coming phase of the course, you will take one of the nodes as a reference node. And so all the other nodes their potentials are measured in terms of that reference. That's why I need only n-1 potentials. And I have m flows, so I have a total of m plus n-1 unknowns, and those are what I'm going to solve for. And Vladimir is going to show you how to solve for that. Any questions before I hand off? Yeah? If the edges cross, what do you mean? If I have an edge between 2 and 4? Yeah, so the critical thing is for you to find the independent rows of the incidence matrix. Once you find the independent rows, notice I can define on this particular graph another loop. I can define this grand loop here. Huh? That's another loop I can define on this very network without even adding the edge that you're talking about. But the claim is that this loop can be written as a linear combination of these two loops. In fact, if you consider a unit flow in this edge, it'll be a unit flow there and a negative unit flow here, right? Because it's going opposite the direction of y2. That means row 1 plus row 4 minus row 2 is 0. And you define this linear combination for this one correspondingly, and you'll find that the grand loop is simply the sum of these two. Notice the arrow in this direction for this loop is the opposite of that loop, so this row cancels. Yeah. But the key thing is for you to recognize how many independent loops you have. Okay, let me help. Oh, mics. Yeah. I'll be around for office hours and stuff. Please come to me today, 2 to 4, in 144 MA. And then I'll be back at the podium for the third phase of the class. After swim break.
Okay, thank you, Babak. So we're going to talk a little bit about circuits in the next, I guess, 5 weeks. And so I want to continue kind of on the thread that Babak started talking about SPICE and kind of what happened at Berkeley about 30 years ago. But before that, I want to sort of give you a context of why we're doing this module. Right? We just did a whole bunch of math. We laid the foundations of linear algebra for some of the very powerful tools that we can use. But if you look at everywhere around you, from your laptops to cell phones to things that you use basically 80% of your working day, they all have underpinnings in essentially electronic systems, which basis you're going to learn kind of in this module, right? So I just want to show you kind of what is that underpinning. We have three blocks that we're going to have in these systems. Right. Okay. The first block is sense. So if you look at your phone, what is, for example, a sensor on your phone? Touch screen, right? So any other sensor? Power button. Any other sensor? Microphone, right? Okay. What do these things do? They input something. What is that? That something is some physical quantity, right? It's, for example, for a microphone, it's basically, they try to convert the changes in pressure that you produce with your vocal cords, right? Or that loudspeaker produces. The change in the sound pressure hits the membrane on the microphone. That membrane vibrates and changes some other physical quantity, which is essentially a voltage or a current. Right? And so, same with touch. With touch, you press the button or the screen, where we'll see actually today one of the mechanisms how we can do that. That pressure causes essentially a change again in one of these two sensing variables, current or voltage, so that the follow-on circuit can actually figure out what's going on and then do some action. So these things here are essentially called transducers. or sensor. So there is some physical quantity here that the sensor will convert to current or voltage. Then we got actually very good at taking current and voltage and then using them to figure out what was actually going on right here. Right? So then we do compute. And today, we exclusively do computation with types of devices that use current or voltage. That's basically, and while I'm describing this, I will actually go ahead and, for the people who came today, I'll hand you this. So this is a 300 millimeter wafer from state-of-the-art foundry of integrated circuits. If you look at your pocket, all your devices, you sum them up, you maybe have this much silicon. So this is silicon. It's basically the most abundant Earth's element, right? So how do you make smartness from rocks, basically? That's what humankind is really good about. And you make it just like you print paper, newspapers. It's basically photomasks. You expose, you lay the material, you then remove it, etc. And like a cake, you basically build up a whole stack. It doesn't look like a whole stack, it's very thin. In fact, the stack is only, let's say, 10 micron thin on top of a couple hundred micron of just base of silicon, right? So I'll hand this around to people so you can take a look. It's glued, so it's okay, you can hold it. But basically, what happens inside these integrated circuits, there's these teeny devices called transistors, resistors, capacitors that are implemented there that pass current and voltage. And they will be able to do some computation based on these quantities. And then, okay, what is that of use to us if we cannot see it? Right? So what has to happen then in this box? Output, right? But output into something that's a physical quantity, right? Physical quantity, even if it's a letter that's displayed on a screen, that's actually light, right, that we see. So we need to produce that. So again, we have, like, let's say a display here. We have a speaker. Right, what else? You can have some tactile feedback, right? There's these new games, gloves and stuff you put on, basically, so tactile. There are also things that are happening right now where what I'm sensing here is actually, let's say, probe. So what I'm sensing is actually a neural signal because I have an electrode stuck in the brain or some neuron in the spinal cord. I sense, again, transduce that to current and voltage. In fact, actually, we do have currents and voltages in our neural circuits. We then compute what was the intention of the brain to do in that particular region, and then we stimulate another electrode to act, right? So not only to recognize what's happening in the brain, but basically to stabilize. If you have a patient with Parkinson's disease, you can actually now have actually little things that you can use to stabilize the tremors and things like that. So these things you will see increasingly also around you, but it fills this generic kind of flow where we have a sensor or transducer, the thing that computes based on currents and voltages, and then another transducer. The imaging module that you did exactly this, right? We had projector that was projecting, we had a circuit that was sensing the light, Our Arduino was kind of then further computing based on these currents and voltages, and then we were displaying it, let's say, on our computer screen to see how well we scanned the card, right? So it's exactly the same process. You'll see it exactly the same on the touch and all of these things. Now the big question becomes, how do we build these circuits that can do these things? Not only how do we build them, how do we create math that can actually do this computation, right? These two things are very interdependent. Depending how I build a circuit, the math that I do here will be different. And that's why we want to teach you in this course that these things are actually connected. You saw in lab 1, depending how you were scanning and how many pixels in a camera you used. With 1 pixel, all your math was kind of dependent on these kinds of things. That's why big companies today, if you look at Facebook, Google, all of them are not just software teams. They have completely integrated teams, from people who redesign the data centers to basically do more energy efficient computation together with software, to people who build like Google Glass. This is a sensor. It has to do some computation and output something. Things like that. Okay. Another thing about this whole flow is that, as Babak started discussing, once I figure out what the circuit is, and I draw it, as you'll see very shortly, we've managed in these 30 years to actually train computers to very simply solve these circuits. Right? So you don't need to be intimidated by the size of the circuit anymore, because ultimately the computer will check it for you. But what do you think is the hard part about this whole thing, if it's not solving the circuit? Designing the circuit. How does one design a circuit? Any ideas? What would be the process? Yeah. Logisim will help you only check what you did, right? But how do you come with the initial topology, right? Yep.
You need like a spec, like something.
Exactly. The first step is spec. So what does that mean? Clearly specify what the circuit needs to do. Doesn't this sound trivial? This is one of the key things in design. If you don't trust me, believe me that many teams in advanced companies still struggle doing this well. Because if you cannot formulate what you need to build, how can you build it? And it's not that easy. It sounds trivial, but once we talk about complex tasks, you simply don't know where to begin. Right? And so people iterate often on this to try to figure out, okay, I'm going to specify it, and then I'm going to the next phase to see how I'm going to do it, and then I see I don't know how to do it. That means I haven't specified it well enough. Right? And then you go back and try to narrow down what you really want to do so that you can craft a strategy. Okay, so the second one then is the strategy or approach. All right, how am I going to do it? Usually for us, this is a bit easier once you know what needs to be done, because it involves conversion of some physical quantity, for example, into currents and voltages that I then can take and process further. Right? So, but it's an important step. What is the third step? What do you think? Once you have a strategy, what do you need to do? Build it, implement it, right? Only here is where you sort of draw your circuit, right? Okay, are we done? I drew it. What then? Revise. Okay, well, you'll be drawing the circuit. How do you know whether you need to revise it? Test it. So test/verify. Key. Okay, this is probably one of the most important tasks, believe it or not. These things that I just handed you, those are called integrated circuits. We're talking about billions of transistors, billions of circuits elements, billions of nodes in the graph, right? And how do you check, what's the probability that you didn't make a mistake somewhere, right, when you were laying them out or designing them? So people today spend more than 50% of the time in this step. 50% of the whole engineering team is just testing what others have done. And they still cannot have full coverage. Okay, so that's how complex this step is. So always make sure to do this. And then often you'll have to sort of come back, potentially even to step one. Right. Okay, so this is kind of a little bit dry, but we're going to test it out immediately on an example. Right. So let's say we looked at this over here, and the first thing that came to mind is touch. I guess you like your iPads and touch and smartphones. It's a very useful thing. You basically, your fingers are on it probably a few hours a day, right? So let's figure out how that technology came about, right? And how we can basically go and design one of these. So in this same spirit, I have some physical quantity. I want to turn it into current and voltage. Let's draw a diagram for this particular thing, right? So what do I feed into this system? Right? What are my fingers doing when I'm pressing? It's pressure. Pressure at some location, right? At, let's say, XY location. Right? Okay. I need a transducer to give me current or voltage, because I know my circuit needs that to be able to work. Right? I need another block that will take these values and compute. What do I need to compute? What do I need to extract from this physical information? Position. So I want to know x and y. To know x and y, how many variables do I need? 2. So in whatever physical world, system, intermediary, mechanical, optical, electrical, I need 2 independent variables to show me x and y. Right? So I can do Ix, Iy, I can do Vx, Vy, I can do sort of any combination of these, as long as they're independent. Right? Okay, so let's try to think along these lines. How do I create something like this? Now, one of the tricky things, because now I'm about to go into a design step. I need to synthesize something that doesn't exist. I can't do it out of nothing. Right? I need to have some background. And background is usually comes from physics or some patterns that you've already learned work in certain ways. Let's go to make it kind of analogous to math, you need to know kind of the operators. Right? So here I'm going to basically just try to think in terms of some things that I can find around me. Right. So let's say a wire. Right? A wire is a pretty common thing I can find around. Right? So let's say we take a wire and look at its properties. A wire has a cross-section A, some length L, and has basically a physical property that's called resistivity. All that means is basically when charge flows through that wire, how hot does the wire get? Because essentially what's happening is charge is flowing through the wire. There are atoms in that wire. Right? And then the charge will be hitting those atoms and essentially delivering to them some kinetic energy or some of its own energy as it's flowing through. Charge will slow down and the atoms will get excited and start vibrating. As the atoms vibrate, they emit phonons and basically the whole thing starts heating up. Right? So if you want to try this, you can basically go take a 9-volt battery in a pickle and like try to run some charge through it and you'll see it heats up. Or in your little breadboards, pick a very small resistor value and add it to the battery and you'll see what happens. We'll cover that a little bit more formally here when we talk about energy and power. But basically, any material gives resistance to charge flowing through it. Okay? And now, that would mean I can characterize that with some constant, which is called resistivity. And I will be able to also characterize this constant for a given physical wire by basically this relationship. This is the resistivity of the wire, the length of the wire, and the cross-section of the wire. And what this means is the longer the wire is, statistically, the more likely for my electron or piece of charge to hit some atom in that wire. So, and you lose the energy. And if it loses the energy, it will heat up that wire. The smaller the cross-section, again, more likely for the electron to basically go and hit something in that cross-section. Think about it this way. If I have a constant number of electrons that are flying in, and I have this huge cross-section, the density of these electrons per unit area will be smaller. But the number of atoms in the wire will be the same in that cross-section. So the likelihood that I'm going to hit an atom is less. So that's, if the cross-section is larger, I have less, with same amount of charge, I have less likelihood to hit something, so I can just cruise through. Right? That's why with increased area, the resistance will go down. Okay. This is just a little bit of the physical properties, but one of the key things I can use in this is that a shorter wire gives me less resistance. Longer wire gives me more resistance. Okay. That's the only thing basically I need to know to start my design. So let's see how I can do that. Let's say I have a plane, just a metal sheet, like on the back of my phone. Okay. And then what I do is I put this wire right on top of it. So maybe we can use a different color for the wire, right? So this will be my wire. It goes right on top of the phone. Now, if we look, this is the top view, right? So I'm going to label it top view. Side view is I have the metal plate, and then I have my wire that sits on top of it. Right? So I'm just looking like from the side of the phone. Now I take my finger and I push into the screen. We're doing one dimension right now. I'll show you pretty quickly how we'll expand into other dimensions. But I just go and push on this wire, anywhere on the wire. Okay? Imagine here, in between, I have some squishy material that can actually move as I push. So let's say I push here on the wire. What's going to happen to the wire? It's going to bend, right? It's relatively thin compared. So let's say I will now draw my finger here. Okay? And as I push down, the wire will bend. And I will push down until the wire bends completely and touches the back plane. Okay? So now I have a long piece of wire from this point to this touching point, and then a short piece of wire from that touching point to the end. Okay? The information about where I touched, where is it contained? Let's say I want to know this coordinate x. Right? Let's call it x naught. Right? If this is 0, how do I determine x naught? What do I need to know about the wire? Okay, resistivity, but like, what I need to know is basically how much of the length of the wire is on this side versus that side, right? Or of the whole length. So x0 to x0 will be, let's say, this length, L1. And from this point on, I would have L2, which would be total length of the wire minus L1. Okay, does this start to look like a circuit? Anyone? Let me give you 1 minute to talk to your neighbor, see if you can come up with a design now. I gave you a little prompt, right? But not fully. This is a symbol we're going to use for the resistor. Squiggly means a charge can't just flow through straight. It kind of has to curve and bump a little, right?
Can you do that again?
Bump a little. Okay, any ideas? I showed you an element R, right? That's the only circuit element we've learned so far. It's a resistor. So I take a piece of wire of certain length, I will know what's the value of that element, of that resistor. Right? Or how hard it is for current to flow through that resistor. Right? So if I have this wire, now in two pieces, how can I represent it? Yes? Okay, as two resistors, right? So let's maybe do like a side view of the wire again, right? This is the point I'm touching, right? So this length is L1, this length is L2. I can represent this piece of the wire as a resistor R1, and then this piece as a resistor R2. Right. So let's see if this actually checks out, right? I know that my total wire resistance is rho times L over A, where L is essentially L1 plus L2. That's my total length of the wire. So I'll just write this as rho times L1 plus L2 over A. Or I can separate it out. Right. Here, this is R1, and this is R2. So the total resistance of this wire is the sum of these two resistances. So if I change the location of where I'm touching, what is going to change in this? Out of these three quantities, R, R1, and R2. R1 and R2 are going to change, but the sum is not going to change because my length is constant, right? So I'm going to use that. Okay. Now, I only showed you the two resistors, right? We've seen that in R2, R2 contains this length information, right? It's right here. That's my coordinate I want to take. R1 also contains the length information. So if somehow I could read out what these resistances are, turn them into currents and voltages, then I'm done. Right? I satisfy this first box. Right? So in this box, in this resistive touch screen, I would turn R1, R2 into current or voltage. I want to turn these values into current or voltage because these values of R1, R2 give me the coordinates. Right? Okay. What other element do I need to do that? I only have resistances, right? What else do I need to be able to generate or have currents and voltages in the circuit? Power. Everyone needs power. You eat breakfast in the morning, right? Okay, so as Babak was saying, kind of on the mountain kind of analogy, I don't know if anyone went to Tahoe last weekend. You need something to get you to the top of the mountain so you can ski, and that something then has to take you again to the top of the mountain, and then you ski down, right? Same with charges. Charges in a circuit need somehow to get to the higher potential node and then kind of slide down. Right? So we're going to need, I'm going to first draw it crudely, and then we're going to see a symbol, right? We need a battery. Right? Battery stores some energy in it, in form of, let's say, chemical energy. Right? Now, in order to use it in the circuit, we will attach some circuit elements to it, let's say a resistor. Right? But to understand how battery can generate voltage for us, we first need to understand what's the relationship between voltage and energy. Right? So voltage, as Babak was saying, is kind of, you can view it as a difference in the potentials. Right? So if I have some charges here, let's say plus minus, these are some random charges somewhere. If I take a positive charge from point A and I want to move it to point B, I need to put some energy into it. Okay? And so that energy, so that the difference in potentials between these 2 points, so let's call that UB minus UA, will be equal to the amount of energy I have to put in over the quantity of the charge that I'm moving. Okay. This difference in potentials we're going to call voltage. Does it matter what's the absolute value of these two potentials? If I have one potential of 1,000,000 and another one of 1,000,001 volt. versus 0 and 1. Does it matter to that equation? No. That's exactly this thing that Babak was talking about earlier. It all depends what's your point of measurement. If a ski lift is going to move you from the base of Heavenly all the way up, it's a certain number of feet of height, right? But it's also a different amount if you're talking about from the sea level, right? So depends where you define these potentials from. We really will only care about voltages, which are the differences in potentials, right, in our circuits. And these points that we're talking about are actually nodes. So if in a battery, I'm going to draw this as a voltage source, like this, right? And we'll have a node A and B. And I'll label it as V source. Vs will give me some number of volts. So for example, we'll say Vs equals, let's say, 5 volts. Right. V here is for volt. Fortunately, there are not that many units that are left. If you become famous, you get one of the physical units. So we have volts for voltage and potential. What is the unit for energy? Joule. What is the unit for charge? Right. Okay. So we have our battery. We know it stores energy. Okay, this is not possible to take this one down. So let's draw our circuit. I'm going to draw only one resistor here first. Okay? That's our whole wire. We know that wire is some resistance R. And this battery has some voltage Vs. When we draw it like this, when I draw it like this, it's called ideal voltage source. I'm going to say ideal voltage source. That means I'm assuming that this battery will give me a voltage Vs at any cost. What does cost mean? I could be draining as much current from it and will still keep giving me the voltage Vs. It's very important, as you'll see later. Not all batteries can do that. In fact, many can't, simply because they have some internal resistance. We'll see that shortly. But at some point, I need to assume there is some ideal element that gives me this, and then I can add all the other non-idealities to it. So an ideal voltage source, although it does not exist in nature, will be keeping a fixed voltage regardless of the amount of current I that flows out of it, right, or into it. Doesn't matter. Current can be positive, negative, whatever. It keeps voltage across its terminal as Vs. Right. So I'm going to draw this circuit this way. One key important thing I want you to basically remember is that often you'll see in books, and actually even in this course and in problem sets and everywhere, sketches of circuits that really irritate you from the graph mathematical standpoint. Okay? How many nodes does this circuit have? 2 nodes. Let's label that node, this node A, this node B, right? Or 1 and 2, whatever. I can draw this circuit a million different ways, and it will still have 2 nodes, but you'll be confused utterly, right? As I'll show you later in some examples. When you're confused by how the circuit looks, always go try to find where the nodes are. And just draw all the circuit elements between these nodes. And we'll be doing that a little bit just so you can get the feel, because that's exactly how computers go and solve things in the end. We'll be showing you the more formal framework based on what Babak was showing on the flows and graphs. But sometimes circuit designers don't have the patience to go and do all this, so they take shortcuts. Because our goal is not really going to be to formally solve circuits. It's going to be to synthesize quickly some designs. And in these things, we like to see some patterns, right? And then take shortcuts. But initially, until you become sort of a Jedi apprentice and then a master on circuits, feel free to always simplify it to a graph and then start seeing these equivalences or patterns. Okay. So here we have two nodes. I'm going to label the voltage AB like this. I'm not going to use pluses and minuses. The reason is I don't care about the sign of anything. I really don't. And remember, in circuits, you shouldn't look at the signs of anything. Things are always relative to how you define them. The reason why I'm labeling it like this is I'm interested truly in the potential difference between this point and this point. See how I was defining as the charge moves from point A to point B, right? So that exact arrow is what I'm drawing over here. That represents that voltage, AB. And for reasons I'm going to show you in the next class, I'm going to label the current through this branch, I, let's say I1. I'm going to label it going into this arrow on a resistor. We're going to call that passive convention. I'll show you next time why it's passive. It has to do with power. Okay? And the fact that this guy actually just dissipates power, it cannot produce energy. But I'm going to draw it like this, and we're going to stick with this convention. Right? And then for the sources, I can do whatever I want. Okay? I can label this current, let's say I label it like this. So this is I0. Do I need to label any other voltage in this circuit? What do people think? Are there any other nodes? I kind of drew that arrow here. I could have drawn it like right here, VAB, right? It's the same thing. It's the same thing because this wire here is an ideal wire. It doesn't basically have any potential across it. Think about it. If I have something that changes the voltage, I'm going to draw it as explicitly as an element. Everything else is a connector. It's an ideal wire. Nothing happens along it until it hits the node, right? Okay. So in this circuit, right, what is VAB if I know what VS is? VS produces, its definition is that between points A and B, it produces voltage VS with a plus sign on A. So what is VAB? Okay, so we have negative VS. Does everyone agree with that?
Yes.
Yes. Okay. The VAB is the voltage difference between this potential and this potential over here. The goal of this supply is to increase the potential from this point to this point by Vs. Right. So which one of these 2 points has a higher potential? A. So VAB, remember, it was potential A minus potential B, right? So is it minus Vs or Vs? It is Vs. Right. Now notice on purpose, I'm not putting any reference here. I could have said VB is actually 0. I assume potential UB at this node is 0. Then I just go 0 plus Vs, and I'm right here. And the difference between these 2 points is Vs. Okay. So there is one important thing that I can see on this side happening, and that is that VAB is equal to I1 times R. So this just relates the flow of current through this resistor to how much energy I lose on this resistor. Right. The more current I have flowing through the material, the more electrons I have bumping into atoms, the more energy will be dissipated. And voltage, remember, is our proxy for energy in moving charge. So this relationship holds, and it's called Ohm's law. And resistance, we're going to basically label in units of ohms, current in units of amps. We're almost there. So we have that VAB is Vs, and that over here, VAB is I1 times R. So we have that Vs then is equal to I1 times R. Let me now go and split this R. I'm going to draw the circuit that we actually have in our touch screen. I have R1, and I actually have R2. Now I've introduced another node. This is A, this is B, and this is node C. C is where I was touching, right? If I have a way, I take a terminal out of this whole plane is my node C. Right? Wherever I touch, I connect to this back plane, which is my node C. So that's here. So between C and B, B is the end, so let's say this will be node A, the end of wire will be node B, and this is node C, and I'm connecting a battery between nodes A and B. Right? So let's see how we can analyze what's happening here. I would like to measure this voltage, which is VCB. I also have this voltage, which is VAC. And I have this voltage over here, which is VAB. What's the relationship of these three voltages? Think about it in terms of heights, right? Exactly how I drew it. So VAB equals VAC plus VCB. I like to do it this way. You can also just draw a loop and go around. That's called Kirchhoff's voltage law. If I draw a loop and I go around, I will say VCB plus VAC minus VAB equals 0. It's minus because my arrow is now hitting this arrow first. Right? So it's just a convention. I don't like to write it this way because it's kind of, I have minus signs and stuff. Here I kind of see one height equals the other. I'm done, right? Okay, so this is going to be useful to us. But we also need these currents. So I'm going to label them as I1 and I2, again, going into the arrow. Now, I already know that VAC is I1 times R1. That was just like I did it over here. VAB was this current times this resistor. Right? It's just Ohm's law. For this element, the voltage across it is the current into it times that resistor. Same for this one at the bottom, right? So I have that VCB is I2 times R1. Now, if you remember what we talked about at the beginning of the lecture, or also last lecture, current going into the node. Yes? Yes, thanks, Babak. R2. The current going into the node has to be the same as the current coming out of the node. The node doesn't hold charge. So whatever comes in must come out. So I1 then has to equal I2. So all I need now is basically these two equations and this one over here. These two currents are the same. So I can rewrite this equation. Okay, let me do it here. VAB, I'll write VS. VAC, I'll put I1, R1. And then VCB is I2, R2, but I will use I1 because they're basically the same, right? Now I can take out I1, just have R1 plus R2. Okay, this is kind of trivial. If you go back to what we did here, we know that this R is the sum of the resistances, right? So it's basically the same thing. But I also have one more thing, that this voltage here that I want, VCB, is I1 times R2. Why I1? Because both currents are the same. Okay. So notice now what I can do. I can eliminate I1 from this first equation. Right? So I can write this as Vs over R1 plus R2. I got this piece from this equation times R2. So why is this significant? Well, can anyone tell me what this means? What have I done here? Talk to your neighbor for 30 seconds. Yes. Why is? Oh, okay. So I1 is in this branch, right? So I1 enters node C. Current through a single branch. Remember, a resistor is in this graph branch, right? The current that comes into the resistor must come out of the resistor. Otherwise, the resistor would go boom, right? Resistor doesn't hold charge, right? Whatever comes into the wire comes out of the other end, right? The voltage across the wire is, in order to push the current through this resistor, you need the voltage across the wire, right? So the potential along the wire will be different, right? If you take the wire and slice it into a lot of small wires, right, the potential along the wire will be changing, right, until it adds up to the total voltage that you have across the wire, right? But the current is like a river; it's constant. Right? Okay, so just for maybe some people who were still confused. The current that flows into the resistor is the same as the current coming out of the resistor. It's still one branch of the graph, right? All the way until we hit node C. Then in node C, we say, okay, is there anything else coming into this node, right? Because multiple edges could be coming in. In fact, edge 2 is coming out, right? Okay, going back to here. What did I do here? Any volunteers? Yes? That's right, but did I get some physical quantity that I wanted? I was looking for a coordinate. Did I get it? Yes? It is encoded in R2, right? Remember, R2 is L2 over A over this R total is rho times L over A. So I'll cancel these, and I have my L2. Now I've encoded my position along the wire into the voltage that I'm reading out. All I need now is some magical circuit to read that voltage and compute it, process it. Let's say you can go and with this make a little basically instrument where a note is proportional to the voltage you're getting along the wire you're pressing, right? Okay. Another key thing that we've done here is we have defined an operator here. An operator is called a voltage divider. And this is the first operator basically in circuits that you're going to be using. I take the supply and I divide this supply voltage across this resistor. And that is proportional to the magnitude of this resistor over the total resistance that this voltage sees. Okay? So next operator, next class. Wafer, hopefully someone can bring me the wafer. Yeah. Thank you.